So for today, we're going to learn the last topic, which is first order differential equations known as Bernoulli's equation. And this particular equation is normally discussed right after linear first order differential equation because in terms of form, they are quite similar. And they actually have only one difference, and you get to see that later. So for a Bernoulli equation, we need only to look into the form, or if the form is not yet in this written in this manner, you have to make sure that if you want to solve a DE using the procedures here below, you have already established that it is a Bernoulli's equation. So you still have the derivative, and you still have the product of p of xy, just like in linear DE. And on the right side, aside from the q of x, you will have now the y raised to n, where this n should not be equal to 0 and should not be equal to 1. So the only thing that differs the Bernoulli's equation from linear differential equation is the y raised to n multiplied to the q of x expression on the right side. So again, the p of x and the q of x can be constants or expression which are solely dependent on the variable x. So let's have the two steps here simplified in finding the solution of the Bernoulli's equation. First step is you determine the integrating factor, and that is the e raised to the quantity 1 minus n times the integral of p of x dx. The difference of this phi integrating factor from that of the linear DE is the quantity 1 minus n here. Without this, you are actually solving for the integrating factor of a linear first order DE. After you have determined the phi, then you just follow this formula. You have y raised to 1 minus n. This is your unknown function. You raise it to 1 minus n. N being the exponent of the unknown function on the right side of the DE. Then multiply it to the integrating factor you determined in step 1. Equate it to 1 minus n again, integral of q of x, whatever is the q of x here, times the integrating factor phi. Now, let's apply this principle in the example here. So, your DE does not really look like a Bernoulli's equation. It's far from being one, but you have to first and foremost establish your derivative. In this case, you will have two options. It should be a dx dy or a dy dx. As to which of the two you will use, this is the guide. Of the two differentials that you have, the one that has the simplest coefficient will be the upper differential, and the complicated one in terms of coefficient will be the lower differential in the derivative of your differential equation. So in this case, you shouldn't have a dx dy because dx is complicated in terms of its coefficient. So the one that is less complicated is written in the numerator. So that should be in this case dy, and dx should be in the denominator. Now, if you wish to isolate the dy dx, then the 2x here should be gone by division, and this expression here also, same thing with this. So that's what we do. We isolate the dy dx, and this expression here, we divide by 2x. It's just like we transfer like this, okay? But it's still odd because we're not transferring any of this in the other side of the equation. We simply divided that way. In here we divided by dx, in here we divided by 2x. So that remains this one to be expanded. So you have 6y cubed minus xy rather minus y. And then the 2x here. Still doesn't look Bernoulli. So you have to look for that particular unknown function variable whose exponent is greater than 1. This one is y raised to 3. So that should tell you that this one, together with the divisor here, should be transferred on the other side. So if you're going to transfer this expression, 6y cubed divided by 2x on the right side, that should be a 3y cubed over x. So a negative because it's coming from this side transferred to the other side. Now this one would be negative. We factor out the common y. That's the common y. And the factor would be x plus 1 and still the divisor 2x. So if you look very closely, class, this is your derivative, this is your p of x, and this is your q of x, and this is your y raised to n. So it's now a Bernoulli's equation. So before it doesn't look Bernoulli, but now it's already Bernoulli. So we determine the integrating factor. The integrating factor is e raised to 1 minus n times the integral of p of x dx. So we copy everything here, including the sign. So negative x plus 1 over 2x, and 1 minus our n here being 3, so 1 minus 3. That should be negative 2. And negative 2 and a negative here should make it positive. And if you're going to cancel the 2's, you will have a 1 plus 1 over x. So if you're going to integral a 1 plus 1 over x, that should be an x plus ln of x. By rules of exponents, it could be e raised to x times e raised to ln of x. This one is an x. So your integrating factor phi in the case of this Bernoulli's equation is xe raised to x. So knowing this, we can go straight to the last part, which is just but you follow the formula which says that the left side of your dE should be y raised to 1 minus n times the phi, and the right side should be 1 minus n integral of q of x times phi dx. So copied, substituted the n. This one is copied, and this is your 1 minus n, negative 2. Your q of x here is negative 3 over x. So it's placed in here, and then another phi. Simplifying, you get to cancel the x here. That leaves you with a 6, negative 2, and negative 3. That's a 6 e raised to x. And that would be a 6 e raised to x plus c. This side would be as is. If you wish to transfer the y squared here, it's just a matter of cross multiplication. This is now the solution of our first order Bernoulli's equation.